I'm Laur Hesse-Fisher, and you're listening to Today I Learned Climate, the climate change podcast of the Massachusetts Institute of Technology. And today we are talking about digging for energy, which is a familiar enough idea. It's what coal, oil, and gas companies have been doing for over 200 years. But there's something else down there, a clean source of energy that doesn't contribute to climate change. And it's not a fuel at all. It's not even something that you can hold in your hand.
Well, so the interior of the Earth is very hot. We have this molten core, and all of that heat radiates out towards the surface and basically passes through under our feet every hour of the day, every day of the year.
My guest today is Professor Roland Horne.
I'm Professor of Energy Science and Engineering at Stanford University, and I'm also the director of the Stanford Geothermal Program.
Geothermal. Literally, it means earth heat. And for billions of years, it's been sitting there under the Earth's crust. A molten stew of energy radiating from the pressurized metals that make up most of our planet. For all practical purposes, this energy is infinite and inexhaustible. What we call renewable energy, like the wind and the solar power that are driving the clean energy revolution today. But in one crucial way, geothermal is very different from solar and wind.
The principal difference between geothermal and wind and solar is that geothermal is 24/7. It runs all of the time. Doesn't matter whether the sun is out, doesn't matter whether the wind is blowing, it just runs all of the time. And that gives it a different position in the energy mix to those intermittent sources. And most importantly, it actually substitutes that same kind of availability that we have from, for example, coal or gas or nuclear.
If you're using geothermal power, you don't have to worry about the weather or when it's nighttime. You don't need batteries or a backup generator or anything else to provide the reliability that we're used to from fossil fuels. So why haven't we been using geothermal all along?
Well, people have been using geothermal energy since the Roman times and probably a long time before that as well. So, there are many places in the world where hot water discharges at the surface, and people have been using it for bathing and, medicinal purposes for thousands of years. But in the modern era, people first generated electricity from geothermal energy in 1904, so the last 120 years or so.
Okay, here's how it typically works. First, you dig 2 holes into the scorching hot rock beneath the earth. You call one hole the injection well and the other the producer well. The injection well is for pumping water underground. You inject it into the rock. You need to choose a rock that has enough pores and cracks to hold this water.
The energy in a geothermal system is contained in the rock itself. And in order to recover it at the surface, you have to sweep that energy out by passing the water through the rock. And that's why you need permeability.
Inside these natural fractures, the water gets very hot. When the water gets hot enough, it rises out through the second hole, the producer well. And at the surface, as the water escapes the intense pressures of the earth, that water turns into steam. And that steam can be used to produce electricity, just like in a coal or a gas plant. The steam spins a turbine, which powers a generator, and voila, electricity.
Then what is left is cooler water, and that is put back in the ground. It gets heated up again and produced a second time. And that same water goes round and round and round.
There's a lot more nuance here, but those are the basics. You drill deep enough to reach high heat, you pump in water, create steam, repeat. Sounds simple enough, right? I mean, it's not simple enough that you can go do it in your backyard, but this is a mature, well-understood technology. Or at least it is in places where the geology is just right.
Geothermal electrical plants tend to be focused in places which have relatively recent volcanism or on the edge of tectonic plate boundaries. So all around the Pacific Ocean, for example, there are many geothermal fields in New Zealand, Indonesia, Philippines, Japan, California, Mexico, Costa Rica, and then down into Chile.
There's also a ton of tectonic activity in the northern Atlantic Ocean and in East Africa. Iceland, which is the home of geysers and hot springs, gets a quarter of its electricity from geothermal.
And Kenya is rather interesting in that almost half of the electricity in that nation is generated from geothermal sources. So they're not the largest in generation, but they're largest in percentage of their energy coming from geothermal.
The leading producer of geothermal electricity in the world is, you want to guess? It's the United States. And nearly all of it comes from just two states, California and Nevada.
The rest of the United States, including the whole of the East Coast, basically has none.
Why? Well, because the rest of the United States and the large majority of the world does not have the right geology. It doesn't have the nice combination of high heat near the surface and open, permeable rocks, which is why, all told, just 0.3% of the world's electricity comes from geothermal. But that's just the story so far. The real opportunity for geothermal might just be getting started. For instance, why limit ourselves to electricity? We need heat too, right? For big things like smelting metals and manufacturing cement, and for small things like keeping our homes warm. So why not get that heat from the earth? In fact, there are places where nearly everyone gets their home heating from geothermal.
The district heating system, like the ones they have in Reykjavik, for example, in Iceland, is just another pipe that comes into your house from the utility. So they have one pipe that brings cold water in the house, and they have another pipe that brings hot water into the house.
This geothermally heated water travels through whole neighborhoods, or in Iceland's case, through almost the entire country. The hot water then exchanges heat with your radiator, boiler, or central air system, heating and sometimes also cooling your home. In Iceland, a lot of that hot water is actually wastewater from their geothermal plants. But that's actually not even necessary. Boise, Idaho has district heating, for example, that takes advantage of naturally hot water underground. Now, these systems, like geothermal electricity, they need really high heat underground to work. But the rest of us can take advantage of geothermal heat too. Because it turns out that no matter where you live, you can get 50 or 60 degrees Fahrenheit right near the surface. And you can use that heat to run what's called a ground source heat pump.
And when I say near surface, now I'm talking about the top few meters of ground. So a ground source heat pump is a system much like an air conditioning unit that you might have in the window of a motel. But instead of discharging the heat into the atmosphere outside, it discharges it into the ground.
You might not realize it, but the way that an air conditioner works is that it's not actually creating cold air to blow into your home. It's actually drawing heat out of your home and then shedding it into the air outside. And that takes a lot of energy because in the summer, the outdoor temperature might be 90 degrees Fahrenheit or more. It's pretty hard to shove more heat into that.
Whereas if you have a ground source heat pump, you're rejecting that heat into the ground, which is actually cool because 3-4 meters into the ground, the temperature of the soil is about the same the whole year round. So in the summertime, you've got very cool ground into which you're discharging your heat. And in the wintertime, you're actually taking heat out of the ground to heat up your building. So it's cheaper even than natural gas. So that's the big advantage.
On average, once it's built, this kind of geothermal is the cheapest way to heat and cool a home. It has a catch, though. If it's not installed when you're building the home, then you have to do some expensive and disruptive digging to add a ground source heat pump later on. So if we can have geothermal heat far away from any hot springs or volcanoes, could we also have geothermal power? Enter Enhanced Geothermal Systems, or EGS.
The technological advances that have made enhanced geothermal systems suddenly the object of enthusiasm have been basically borrowed from oil and gas.
And that's because enhanced geothermal uses some of the same techniques as fracking. You see, EGS is all about making the right geology for geothermal where nature didn't provide it.
So if you have a rock like a big granite tombstone, for example, it's hard to imagine water flowing through that. But if you fracture it, you can actually make cracks through which the water can then pass and then recover the heat from the hot rock. And there are plenty of places around the world where you can drill to modest depths, again talking about 3 kilometers or so, and generate an enhanced geothermal system.
That's roughly 2 miles, by the way, which you might be surprised to hear is modest.
3 kilometers, in fact, is kind of an everyday sort of a well. It gets drilled thousands of times per year in the oil and gas industry.
So just like in a regular geothermal power plant, an EGS project will start by drilling 2 wells into the earth. But those wells don't just go straight down. Deep underground, they turn, making a sort of L shape. And at the bottom, you get 2 horizontal wells running alongside each other. Those horizontal wells are for manipulating the surrounding rock. Inside them, engineers use a combination of steel bullets and pressurized fluid to create fractures in the surrounding rock.
And the fractures kind of take off as much as 500 meters from the wellbore in all directions.
And in the end, you've got the perfect rock for producing geothermal energy. The first commercial project like this just turned on in late 2023 and is now powering some of Google's data centers in Nevada with clean, renewable, and reliable energy from the earth. Already, that company has started drilling a new EGS project in Utah that they say will be over 100 times larger, producing about 400 megawatts of electricity. That's enough to power 400,000 homes.
You know, I've been following EGS systems for 50 years, since 1975, but nobody's really made any money from EGS over that whole time. And to see companies now, raising money and going out for 400 megawatts is very exciting.
Which is really the scale of project that we're talking about when we imagine running our whole society on clean energy. EGS is a young technology. It may not pan out, but the current costs of these systems is showing us that the heat underground might just be as affordable as coal or gas in many parts of the world.
We actually did a study here at Stanford looking at the price of electricity expected from EGS systems nationwide. And if we look at an average cost of about $70 per megawatt hour, that's the nationwide average, then geothermal is competitive with that over more than half of the United States.
So we've talked a lot about clean energy sources on this show, and a lot of them are very exciting. But today, only 2 of them, wind and solar, are both cheap enough to compete with fossil fuels and possible to build in a wide variety of places. Is a third one waiting right under our feet? One that runs around the clock and provides heat for our homes and our industries too?
The Earth contains a positively vast amount of energy, enough to power human civilization hundreds of thousands of times over. But it's kind of that underground energy that nobody ever has heard about. And I think one of the things that is very encouraging right now is that people are hearing about it. And that gives the possibility that it can move ahead in a much more significant way in the near future.
That is our episode for today, but there is a whole lot more of TIL Climate available at tilclimate.org. TIL Climate is a climate change podcast of the Massachusetts Institute of Technology. Aaron Krol is our writer and executive producer. David Lishansky is our audio producer. Madison Goldberg is our new editorial coordinator. Welcome, Madison. Michelle Harris is our fact checker. The music is by Blue Dot Sessions, and I'm your host and senior editor, Laur Hesse Fisher. A big thanks to Professor Roland Horne for speaking with us, and to you, our listeners. Keep up the climate curiosity.